this guy here that I passed out to you, it's also on the website. If you happen to lose this, I'll post it up on the website. But this guy is a summary. It's a summary of your 4 special segments. Now remember, when I say segments, we know that we can extend those segments and make them rays or make them lines. In the Springboard textbook, they usually refer to them as lines more than they do segments, which is fine. We should be able to transfer between those fairly easily. So they have the 4 special segments here, and those are your altitudes. We're going to spend the majority of the class time today talking about the altitudes. Then you've got your angle bisectors, your perpendicular bisectors, and your medians. We're going to get to medians at the end of today's class. Those are your 4 special segments within triangles. The reason they're special is because no matter what kind of triangle you have, whether it's acute, right, isosceles, equilateral, whatever, these 4 special segments, whenever you graph a set of 3 of them, meaning like all of the angle bisectors and all the perpendicular bisectors, whatever, those are always concurrent. What does it mean for 3 or more lines to be concurrent? They intersect at exactly one point. Where should that be? Where should those notes be? On the back. That's what we did last class. You should know what it means to be concurrent. You should know what it means when I say a point of concurrency. That is that one point. And so I've also listed out on this chart what those points of concurrency are for these special segments. Those points of concurrency have special names. You've got the orthocenter for altitudes, and you've got your circumcenter for your perpendicular bisectors, and so on and so forth. And we need to learn not only which special segments create which point of concurrencies, but we need to know their characteristics. How do they relate to the triangle themselves? Is there some relationship between that point of concurrency and the vertices of the triangle or the sides of the triangle? Can it be inside the triangle, on or outside? Like, where does this thing end up landing? All those fun things. And so this chart really does a great job of just kind of condensing all that information into one. So what we're going to focus on today for the chart is the last row, the very bottom row. And so it first starts off here. It says orthocenter, because that is the point of concurrency that we're going to focus on today. We're actually going to locate the orthocenter on a triangle today, and that's your homework. It's part of your homework is to locate what are the coordinates, what are the x and y values of this orthocenter for this triangle. So the orthocenter is created by the altitudes. Now, when you look at the altitude, we're going to take clues from the definition on how to write the equation of these altitudes, because that's what our end goal is. We need to be able to write the equations of these special segments, and then we need to be able to see where do they intersect, meaning what is that point of concurrency. What 2 things must you have when you want to write the equation of a line? What's one thing? Slope. You have to know what is the slope of that line. You've got to know it. Okay? And so there's going to be clues within these definitions that are going to help you with that. They're going to give you clues about what is the slope of these special segments. What's the second thing you must have in order to write the equation of a line? Some point that line's going to go through, or a point that line contains. Now, that could be the y-intercept, but does it have to be the y-intercept? No, it does not. It can be any point on that line. And so we're going to look for clues from these definitions to help us out. Like, how do we write the equations of these special segments? So altitude. If we read the definition of an altitude together, it says altitude, segment drawn from a vertex perpendicular to side opposite that vertex. So that's what it is. And so if we had this triangle here, when you hear altitude, what do you think of? Heights and planes, okay? Because like you're cruising at this altitude, so that's how far above the Earth's surface you are. That's your height. So I said, and that's great, because altitude truly is the heights. It's the heights, yes, plural, heights of triangles. That's kind of weird to think that a single object has multiple heights, but it truly does. It just depends on what is your perspective of said triangle. So for example, if I wanted to consider this triangle, if I wanted to the shortest side to be the base. So this is what it's sitting on, and I needed to measure this triangle's height. Then I would measure from the tip top, and I would go straight down. Because remember, whenever you want height, it's got to be perpendicular to the base, just like when you go to the doctor. Right? Your height, you're perpendicular to the ground. So, if I considered this side of the triangle to be the base, then this long side here would be my height. And it goes from the vertex, and I'm just reading the definition of altitude. Segment drawn from vertex to opposite side, perpendicular to side opposite that vertex. And that's exactly what this distance here, so this would be the height. So this is one of these, this is one of the three altitudes in this one triangle. But if I change perspective, I said, well, I don't want this to be my base. I want this longer leg of this right triangle to be the base. I want this to be the base, so I'm going to consider this. Okay, well now the height is a little different. Now the height is, it's still the same concept from the tip top, straight down, perpendicular, but now this is my height. My shorter leg is now my height, if I consider this to be my base. And so this is a second altitude of this triangle. And then finally, if I want to consider the hypotenuse of this right triangle to be my base, I say, okay, now it's going to sit here, and I need to know how tall this triangle is. Well, that would be your third altitude. Then you just read the definition, follow the definition. Start at the vertex and draw a segment perpendicular to the opposite side. So this third altitude is right here. It's that segment. Okay? Now sometimes these altitudes will be outside of the triangle. And you've seen diagrams like this before, maybe in 7th or 8th grade, maybe even freshman year, I'm not sure. But this is a very popular question on standardized tests. And so if you look at your chart on the far right, in this last column, it talks at the top, it's labeled inside, outside, triangle. Basically asking, where is this point of congruency going to end up? For some of them, they will always be inside the triangle. However, like for the orthocenter down here, it can be inside, on, or outside. If you have an acute triangle, which is like the one that we have drawn in our springboard textbook on page 192 that we're going to mess with in a second. That's an acute triangle. That means the orthocenter is going to be inside that triangle. If you have yourself a right triangle, then that means it's going to be on this triangle. It's literally going to be the vertex of your right angle, because this leg and this leg, those are two of your altitudes, because they're perpendicular to one another. And then your third altitude has to go through that vertex. So this is the orthocenter of this triangle. It's right here, this vertex of your right angle. Then, if it's obtuse, what's going to happen is that your, so if I start from vertex, this is my perpendicular bisector, but this orthocenter, I would have to extend all of these lines out. And if your triangle is obtuse, that was terrible. It's going to intersect outside of the circle. So that's what it means by it says if it's obtuse, your orthocenter is outside. So we have to understand, where can this orthocenter be? Alright, so let's dive into this activity. Our end goal for 14-1, this lesson, is to be able to determine the coordinates of the orthocenter. We need the x and the y value, where that point is, what its x and y values. We're going to first find it out by graphing. We can graph lines pretty well, hopefully. Then we're going to do it algebraically. How do I algebraically determine if two lines intersect, and if they do intersect, what is that point of intersections? Like, what is the x and y values? How, in algebra, how did y'all do that? Algebraically, that's graphically, that's geometrically. If your teacher gave you two equations of lines, and he or she said, solve this, You got an X value and you got a Y value. I hope and pray that they told you what you were doing rather than just you followed steps and you're like, well, okay, this is my answer. I hope you know what you were doing while you were doing that. Emily, because you remember. Emily, what's up?
It's a system.
It's a systems of equations. When you were solving those systems of equations, you probably first learned by graphing, and you graphed those two lines and you saw where they intersected and you're like, hey, cool, that's my point of intersection. And you wrote the X and the Y values down. Then your teacher may have shown you via calculator and you plugged it into the Y equals and then you could see where they intersected. It was the same thing though. You were graphing these lines and you used geometry to see and to prove visually that those lines do intersect. Then you started doing it algebraically. What were the two methods that you used to solve systems algebraically? Substitution was one of them, and elimination was the second. And you used substitution and elimination to solve those systems of equations. You were algebraically determining the coordinates of the point of intersection. So once we have these equations of these altitudes, then we're going to solve algebraically. All right, so let's dive into it. What they're doing, what the Springboard textbook is doing on page 192, is slowly walking you through, step by step, how to determine the equations of these special segments. What I'm going to do on a test is I'm going to give you the 3 vertices of a triangle. I'm not going to graph it for you. I'm going to give you the 3 vertices of a triangle and say, okay, A is at 0, 1, B is at 5, negative 7, C is at 0, 7. Determine the orthocenter. Go. And you're going to have to know how to get there step by step. On page 192, that's exactly what they're doing. They're showing you step by step how to determine the coordinates of the orthocenter. So if this were a test, this is what Mr. Niven's test would look like. Given the 3 vertices of a triangle, point A at 0, 0, point C at 12, 24, point G at 36, 0, locate the orthocenter. This is what you would do. First step, determine the slopes of the 3 sides of triangle AGC. So please go ahead and find the 3 slopes of triangle ACG. Now I'm going to go ahead and write them off here. You can write them underneath item 1, but I can't scroll and I can't move around like y'all can. So all my information for this entire page is going to be all up in her. Okay? You need to spread it out. Spread it out a little bit.